Right now, entire swarms of galaxies, clusters so massive they each contain thousands of Milky Ways, are hurtling through space at nearly 2 million miles per hour. But here's the mystery. They aren't racing toward anything we can see. They're being pulled toward something invisible, something colossal, something that defies all explanation. Astronomers call this the Great Attractor. And if you think the observable universe shows us everything, think again. We live inside a fragile bubble, a cosmic sphere stretching 93 billion light-years across. To us, it feels infinite. Every galaxy you've ever seen through the Hubble telescope, every nebula painted across astronomy books, every twinkling star above your head lives inside that bubble. But in truth, this entire vast expanse is only a speck, an island surrounded by a far greater ocean we cannot yet touch. Beyond our horizon, other universes may spark into existence like fireflies in the dark. Cosmic strings, hypothetical filaments of pure energy, may slice through reality itself like invisible swords. Some physicists even suggest white holes. The reverse of black holes could be out there, pouring entire galaxies into being. If you are ready to step into realms that shatter reason and twist reality, hold on, because the journey begins with a number that seems to break the human mind. 93 billion. That's the measured width of our observable universe, the part we can see from Earth. But here comes the paradox. The universe is only 13.8 billion years old, born in the moment of the Big Bang. Light, the ultimate speed limit of reality, can only travel 1 light-year per year. By that logic, the farthest we should be able to see is 13.8 billion light-years in any direction. So why does our cosmic bubble stretch nearly 7 times farther? The answer reveals the first clue about the hidden universe. It isn't that light is breaking the rules. It's that space itself is expanding. Imagine a balloon covered in tiny dots. As the balloon inflates, the dots spread apart. The dots aren't moving across the surface. The balloon itself is stretching beneath them. That's our universe. When light left some of the earliest galaxies 13 billion years ago, those galaxies were much closer to us. But over the eons, space expanded, carrying them far away. By the time their light reached us, those galaxies had been dragged to distances of tens of billions of light-years. That's why we now see them perched on the edge of our 93 billion light-year horizon. Inside this cosmic bubble, astronomers estimate we can see about 2 trillion galaxies. Each of those galaxies contains hundreds of billions of stars. The total number of stars within our observable universe is so staggering that if you tried to count them one by one, even at a rate of 1 star per second, you would run out of time. The universe itself would die before you finished counting. And yet, all of this, the trillions of galaxies, the endless stars, the nebulae and quasars, is only what lies inside our observable bubble. Everything beyond that limit remains unseen. The barrier blocking our view isn't made of matter or walls. It's made of time itself. Light from beyond 93 billion light-years simply hasn't had enough time to cross the expanding void and reach our eyes. Somewhere out there, galaxies shine, black holes consume, planets circle alien suns, but their light is still traveling, racing toward us across impossible distances. Millions of years from now, our descendants may glimpse them for the first time. Think of standing on the shore of an ocean. The horizon seems like the end, but you know it isn't. Beyond it lie continents, islands, entire worlds you cannot yet see. That's our universe. The horizon is only a limit of sight, not of reality. And just when you think this truth is overwhelming enough, we slam into something even more mysterious: the Wall of Fire. Roughly 380,000 years after the Big Bang, the universe ignited in a blaze unlike anything you can imagine. The cosmos wasn't stars and galaxies yet. It was a furnace, white hot, glowing at 10,000 degrees Kelvin and beyond. Electrons, protons, and photons smashed into one another in a chaotic soup of energy. Light itself was trapped, scattering, endlessly, unable to move freely. If you stood inside that young universe, you would see nothing but blinding fog. Space was opaque, like the heart of a star. But then came the great cooling. As the universe expanded, the particles slowed, and, for the first time, atoms formed. Electrons clung to nuclei, and light, after nearly 400,000 years of imprisonment, suddenly broke free. In that instant, a brilliant flash of radiation flooded the cosmos in every direction. That ancient light still surrounds us today. It is called the cosmic microwave background, a faint afterglow that we can still detect with sensitive instruments. It forms a glowing shell around us, a wall 93 billion light-years away, marking the very edge of what we can ever observe. No telescope will ever pierce it, because beyond it lies the opaque furnace of the infant universe. And here's the strangest part. This cosmic afterglow looks almost perfectly uniform. Its temperature varies by only a few millionths of a degree. That shouldn't be possible. Regions of space separated by billions of light years, regions that could never have communicated or shared heat, somehow ended up at the exact same temperature. It's like filling a bathtub with scalding water from one tap and ice-cold water from another, only to find the entire tub instantly at one perfect temperature. Something impossible must have happened in the earliest moments of the universe, something beyond our current physics, to smooth it all out. And that hidden process may hold the key to what lies beyond our cosmic bubble. Because if the observable universe is just the nearest room in an infinite cosmic mansion, then the rest of that mansion is waiting just out of sight beyond the wall of fire. Yet here's the unsettling truth. This staggering collection of galaxies, 2 trillion of them inside our observable bubble, represents essentially nothing compared to what lies beyond. Picture it. The observable universe extends 93 billion light-years in every direction, a sphere containing every quasar, every nebula, every faint glimmer captured by Hubble or James Webb. This bubble is our prison of sight. Now imagine leaving Earth and traveling to the very edge of this sphere. From that new vantage point, you could turn outward and see another observable universe, another 93 billion light-year wide bubble filled with galaxies that we will never see from Earth. Some of those galaxies would overlap with the ones in our current view. But vast regions, hundreds of billions of light-years of stars and worlds, would remain utterly unique. To an alien astronomer perched at the edge of our bubble, the night sky would be filled with galaxies hidden forever from our eyes. Shift again. Another 93 billion light-years farther, and yet another new sphere of stars unfolds. Step after step, the cosmos reveals itself as an endless chain of overlapping horizons. Basic geometry proves something profound. The universe is not just large, it is either effectively infinite or so unfathomably vast that infinity becomes the only way to describe it. And this isn't speculation. The cosmic microwave background radiation, that ancient afterglow of the Big Bang, shows us something startling. On the grandest scales we can measure, space appears flat. Flatness means no curvature bending space-time back on itself. It means the universe doesn't wrap into a closed sphere. And mathematically, that flat geometry suggests two possibilities. The universe is infinite, or it stretches so far beyond our view that infinity is the only practical description. That conclusion carries a chilling implication. Somewhere beyond our cosmic horizon, galaxies identical to the Milky Way orbit monstrous black holes. Planets with Earth's size and composition circle suns indistinguishable from our own. The laws of physics that built our solar system have repeated themselves countless times in regions we will never observe. Somewhere another Earth may exist, spinning under a familiar sky, forever hidden from us by the tyranny of distance. But here's where the universe becomes even stranger. The galaxies at the very edge of our horizon are already rushing away at nearly the speed of light, carried on the stretching fabric of space itself. Beyond that edge, galaxies recede even faster. So fast that their light will never reach us. No matter how long we wait, no matter how advanced our telescopes become, those galaxies are gone. The cosmic expansion works like a one-way mirror. We can see out to a limit, but we cannot communicate back. The galaxies we glimpse at the brink of visibility can never see us in return. And every passing second, thousands more galaxies slip beyond the point of no return, lost to us forever, carried away by the silent rip of expansion. But then comes a discovery that cracked astronomy wide open. In 2008, a team of NASA scientists, led by Alexander Kashlinsky, made a disturbing observation. Galaxy clusters, entire swarms of galaxies weighing quadrillions of suns, weren't behaving as they should. According to the standard model of expansion, these clusters should drift apart evenly, spreading like dots on an inflating balloon. But the data showed something else. Hundreds of galaxy clusters were streaming together, rushing at over 2 million miles per hour toward the same patch of sky. Billions of light years apart, yet all moving in lockstep, as though tied to an invisible rope. The phenomenon was christened dark flow. Unlike dark matter or dark energy, which shaped the universe in predictable ways, dark flow seemed to act with terrifying specificity. It wasn't pushing galaxies apart, it was dragging them, yanking entire clusters toward a mysterious location between the constellations Centaurus and Vela. Here's the most disturbing part. Kashlinsky's team calculated how much gravity would be required to produce such motion. The answer: nothing inside our observable universe is massive enough. Not all the galaxies combined, not all the dark matter halos, not even the largest known black holes. The tug must come from beyond the wall of sight. It's like watching leaves float down a river. You see their motion, but the waterfall driving the current is hidden around the bend. The leaves are galaxies, and the unseen waterfall lies outside, our observable cosmos. So what lies beyond? Some theorists believe dark flow is the scar of cosmic inflation, the moment just after the Big Bang when space itself ballooned faster than light. During that brief era, massive structures, dense beyond comprehension, may have been hurled beyond our reach. Imagine clumps of matter heavier than millions of galaxy clusters, stretching across regions larger than our entire observable universe. Invisible now, but still exerting their ghostly pull across cosmic gulfs. Other theories go further. Some suggest cosmic strings, infinitesimal defects in space-time left over from the birth of the universe, slice through the cosmos, bending gravity in ways we cannot yet understand. And still others whisper of parallel universes where the gravity of other realms leaks into our own, dragging our galaxies toward theirs. The truth remains bitterly debated. Some studies suggest dark flow might be a mirage of flawed data. Others, equally rigorous, insist the signal is real. For now, the jury is split. But if dark flow exists, it points to something staggering, a hidden realm of unimaginable mass and scale tugging on our universe from beyond the horizon. And perhaps that isn't the only scar of a larger cosmos. Because deep in the constellation, Eridanus, astronomers found another anomaly, one so bizarre they called it a cosmic bruise. A region of sky spanning 1.8 billion light-years appeared unnaturally cold, containing nearly 100 times less matter than expected. This so-called CMB cold spot is like a wound in reality. In the afterglow of the Big Bang, where radiation should be smooth and uniform, the cold spot is an inexplicable void. Random chance cannot explain it. It's as if something reached through the fabric of existence itself and scooped out a piece of the universe. Imagine dropping a stone into a perfectly calm pond. Ripples race outward in perfect circles, each wave a memory of the impact. Now, picture walking to the far edge of that pond and finding an eerie, dry circle, no water at all, surrounded by ordinary ripples. That empty patch is what the cold spot looks like in the cosmic microwave background. A strange silence in the afterglow of creation, a bruise on space itself. Astronomers first mapped this anomaly in the constellation Eridanus. It spans a staggering swath of sky, and along its line of sight, the universe seems underfilled. Fewer galaxies, less matter, a temperature dip too deep to shrug off as random noise. It's as if something reached through the young universe and pressed a thumb into the fabric, leaving a chill where there should be warmth. The boldest idea blames a collision, not between galaxies, but between universes. In the theory of eternal inflation. Our cosmos is just one bubble in a vastly larger, ever-inflating multiverse. Most of that multiverse keeps expanding faster than light, but in scattered patches, the inflating field decays, and a bubble forms, hot, dense, and primed, to become a universe like ours. If two such bubbles formed near each other before their walls hardened, they could collide. That impact would compress matter in some regions, thin it in others, and leave a circular scar in the ancient light. Exactly the kind of signature some simulations predict. Teams went hunting. In 2010, researchers reported concentric circles in the microwave background that looked like telltale bruises of a bubble strike. But when statisticians pushed harder, those circles faded into the fog of chance. The Planck satellite, Europe's gold standard map of the early universe, added exquisite detail and still found no smoking gun. If a collision happened, its fingerprint is faint, buried, or stranger than our models. So the search widened. Perhaps the cold spot is the shadow of a supervoid, a vast region with very few galaxies, chilling the background through the integrated Sachs-Wolf effect. Photons that dive into a gravitational well gain energy and then lose it climbing out. In an underdense region, the timing skews, leaving a net energy dip, a subtle cool. Surveys did find a large, underpopulated region along the cold spots. Sightline, big enough to matter, not quite big enough to fully explain the chill. Others push more radical possibilities, extra dimensions that tweak gravity on cosmic scales, small departures from general relativity, or unknown quirks of dark, matter and dark energy. For now, the bruise remains, real, persistent, and unsatisfied by simple answers. To understand why these scars matter, you have to step back to the moment the universe went wild. Nothing outruns light, No particle, no signal, no ship. But space itself isn't a thing that travels. It's the stage, the ruler, the fabric. In the first heartbeat after the Big Bang, that fabric erupted in inflation, doubling and doubling again, an exponential frenzy that expanded regions by factors of roughly 10 to 126 in a blink. Don't picture galaxies sprinting, picture the grid, beneath them stretching. Two ants on a balloon don't need to run for their distance to grow. Inflate the balloon, and they drift apart faster than any ant could move. That distinction, objects limited by light, space free to stretch, solves an old riddle. The cosmic microwave background is astonishingly uniform in temperature across the sky. Separated by tens of billions of light years, those regions should never have equilibrated. But before inflation, our entire observable patch was tiny, close, and communicative, able to trade heat and settle on the same temperature. Inflation then yanked those once neighboring regions apart beyond any hope of contact, freezing in their uniformity and sprinkling tiny quantum ripples that later grew into galaxies. The smoothness of the sky is not a coincidence. It's the fossil memory of a time when everything we can see was small enough to share a breath. Inflation ended here, but not everywhere. In most of the multiverse, that inflating field keeps going, stretching the background emptier and colder. In scattered pockets, the field decays, its energy pouring into matter and radiation. Each decay is another bubble universe igniting. Hot. Plasma cooling into atoms, atoms into stars, stars into worlds. The timing and placement of those bubbles are set by quantum fluctuations, random like radioactive clicks in a Geiger counter. Our cosmos is one such bubble, floating in an eternally boiling sea. The implications are not poetic, they are practical. Because space keeps expanding, and because dark energy is now accelerating that expansion, there exists a hard limit to what can ever reach us. Light from some galaxies still arrives because it left when those galaxies were closer. But any light they emit today from beyond a certain distance will never cross the widening gulf. This defines a cosmic event horizon, roughly 16 billion light-years away in proper distance right now, an edge in time as much as space. Information from beyond it is not merely unseen, it is unseeable, no matter how long we wait. This horizon carves the universe into islands. Within our island, gravity and starlight and life can interact and evolve. Beyond it lie other islands, other skies, causally disconnected forever. Inflation is still minting new islands even now, bubbles budding, off in the inflating deep. Somewhere collisions between those bubbles may be common, somewhere they may be rare. If our sky does carry a bruise from such a strike, it would be the first hard evidence that our universe is not alone. So we circle back to the cold spot, this unsettling silence in the relic light. Maybe it's a supervoid casting a long, cool shadow. Maybe it's a smudge of statistics. Or maybe it's the faint thumbprint of another universe on ours, subtle, circular, and ancient. Whatever the truth, the message is the same. Our map is not the territory. The early universe is still whispering secrets through the static, and we're only just learning how to listen. Right now, scientists believe we are living inside one bubble universe, our cosmic home, a sphere of reality that stretches 93 billion light-years across. But what if I told you this is only one bubble in a cosmic ocean that never stops boiling, where new universes pop into existence forever? Here's the crucial insight. Once cosmic inflation begins, it never truly ends. The Inflaton field, the mysterious energy that drove the Big Bang, creates new space faster than it can decay into matter. That means even though bubbles of universes form constantly, they are just tiny pinpricks in an ever-growing inflating background. Most of reality, almost all of it, remains trapped in this eternal inflation, stretching endlessly. And so, inflation produces not one universe, but an infinite multiverse, where each bubble is a universe unto itself, born in fire, glowing with stars, evolving galaxies, and eventually dying when its energy runs out. Our bubble happens to span those familiar 93 billion light-years. But others, they could be far smaller, vanishing almost as soon as they form, or unimaginably larger, dwarfing our entire observable cosmos. Some bubbles might be rich with matter, blazing with galaxies. Others might be nearly empty voids, and a few, shaped by the quirks of quantum randomness, could run on laws of physics entirely unlike ours. Imagine a universe where gravity repels instead of attracts, a cosmos where light curves back on itself, or even a reality where time runs backward or splits, flowing in two directions at once. The separation between bubbles depends on a cosmic race, the speed of inflation versus the rate of bubble formation. In most cases, space wins. The distance between bubbles stretches so fast that they drift apart forever, each sealed in its own eternal isolation. They will never communicate, never collide. But sometimes, rarely, two bubbles form close enough that their expanding walls crash into each other before the inflating void rips them apart. When that happens, universes bleed together, scar one another, or collapse in cosmic violence. Such collisions may have left fingerprints in our own sky, subtle bruises like the infamous cold spot, still puzzling astronomers. To understand how these bubbles form, you have to zoom into the smallest scales of reality, shrink space down to the Planck length, about 1035 meters. At this incomprehensible size, smooth space-time dissolves into quantum foam, a restless ocean where virtual particles pop in and out of existence in times shorter than any clock can measure. This foam is not a quiet background. It is an engine. It fuels the creation of universes. Here's how it works. The inflaton field has a certain energy value that drives inflation, but quantum fluctuations constantly jiggle that field. Sometimes, in tiny regions, the field dips below a critical threshold. When it does, inflation halts locally. The immense energy-driving expansion converts into ordinary matter and radiation. A bubble universe is born. Elsewhere, inflation rages on, spawning more chances, more fluctuations, more universes. Multiply this probability across infinite space and infinite time, and the result is staggering. Universes are created without end, each one its own cosmic story. Some spark stars and galaxies, others remain sterile and cold. Some are tuned for life, their physical constants balanced like a razor's edge. Others collapse instantly, never producing even a single atom. This is where the anthropic principle comes in. Out of infinite possibilities, we observe a universe where life exists, because only in a bubble like ours could conscious observers ever arise. If gravity had been slightly stronger, stars would collapse too quickly. If it were weaker, galaxies would never form. The laws of our bubble are not inevitable. They are simply one outcome among countless cosmic dice rolls. And if the multiverse is real, then somewhere out there, other bubbles contain versions of you. Identical copies who lived the same childhood, made the same choices, but at some point, diverged. Another you became a teacher. Another never left their hometown. Another never existed at all. The multiverse implies that history itself is not unique, but endlessly repeated and remixed across infinite worlds. Mathematics makes this unavoidable. Physicist Andre Linde, who pioneered chaotic inflation theory, showed that bubble universes form with random properties determined by the wild fluctuations of the inflaton field. The probability of a bubble forming in any tiny patch of space can be written simply as P=1. ETA's time stretches toward infinity, the probability approaches 100%. In plain language, if you give space enough time, a bubble universe will form. Given infinite space and infinite time, infinite universes are guaranteed. It's like flipping a coin forever. Each flip is uncertain, but given eternity, you are certain to see heads, not just once, but infinitely many times. Now imagine flipping infinite coins in infinite rooms across infinite time. You don't just get one result. You get every result repeated endlessly. Bubble universes work exactly like that. And here's the part that twists the brain. Inflation expands space exponentially. The volume of inflating regions doubles, and doubles again every tiny fraction of a second. Even if the chance of bubble creation in a single region is small, the sheer explosion of new space guarantees that bubbles keep forming faster and faster. Like bacteria multiplying in a petri dish, their numbers surge. Eternal inflation ensures the growth never stops. This is the multiverse, an eternal boiling sea of universes, each unique, each real, and each forever unreachable from our own. Imagine reality itself as a cosmic lottery. Every time a new bubble universe forms, the dice of physics are rolled, and the outcome decides whether that bubble becomes alive with galaxies or remains forever dark and sterile. The stakes? Everything. Inside each bubble, the values of the A, fundamental constants, the strength of gravity, the mass of the electron, the speed of light, and the intensity of electromagnetic forces are set at random. They aren't chosen by design. They aren't fine-tuned by hand. They emerge from the chaos of quantum fluctuations as space inflates. And this randomness guarantees infinite possibilities across the multiverse. In some bubbles, gravity is so weak that matter drifts endlessly, never clumping into stars or galaxies. Imagine a universe where hydrogen and helium wander forever as cold gas, spread across a night that never ends. No stars, no planets, no chemistry, just an eternal void. Other bubbles go to the opposite extreme. Their gravity is so strong that stars collapse almost as soon as they form. Nuclear furnaces blaze with unimaginable intensity, but they burn out in mere millions of years, far too short for planets or life to take shape. Even worse, the violent deaths of these stars sterilize entire galaxies with radiation. Electromagnetism, too, is a knife's edge. Increase it slightly, and atomic nuclei, the very heart of matter, fly apart, ripped to pieces by repulsive forces. Decrease it just a little, and electrons collapse into nuclei, destroying chemistry before it can begin. In either case, complexity vanishes. There are no molecules, no DNA, no life. This is why scientists turn to the anthropic principle, the idea that we find ourselves in a life-friendly universe not because it is special in the grand scheme, but because it is one of the few bubbles where observers like us can exist at all. Out of infinite random possibilities, we inevitably exist in a bubble where conditions allow us to ask these questions. Everywhere else, silence reigns. But the story of bubble universes doesn't end with random constants. Sometimes the bubbles themselves collide. Picture two soap bubbles floating in the air. Each carries its own tiny ecosystem. If they touch, their surfaces merge, rippling and warping as they crash together. Now scale that to infinity. When two universes form close enough in space and time, their expanding walls eventually slam into one another with the force of entire realities. Physicists predict that such cosmic collisions create gravitational waves, ripples in the fabric of space-time, that echo forever. These waves would leave scars, permanent imprints in the cosmic microwave background radiation, the ancient afterglow of the Big Bang. Instead of random noise, we'd see circles, rings of temperature fluctuations aligned like shock waves from an unseen impact. Matthew Johnson and his colleagues at the Perimeter Institute ran computer simulations to predict these scars. In 2010, researchers thought they found them. 4 potential ring-like patterns in NASA's Wilkinson Microwave Anisotropy probe WMAP data. For a brief moment, it seemed our universe had literally crashed into 4 neighbors. But the excitement faded. When the Planck satellite produced sharper, more detailed maps of the microwave background, the apparent signatures dissolved into statistical flukes. Random chance had imitated cosmic violence. Still, the search continues. More refined statistical methods are now being developed to filter out noise and isolate real collision scars. If scientists ever confirm such a signature, it would be the first direct evidence that the multiverse is real, that our universe is not alone, and the possibilities go even deeper. Some bubbles don't just shuffle the values of physics. They rewrite the very rules of existence. Imagine a bubble where electrons weigh as much as protons. Chemistry, as we know it, collapses instantly. Or a bubble where gravity repels instead of attracts, causing galaxies to fly apart before they can form. Stranger still, some universes might form with entirely different numbers of spatial dimensions. We live in 3-dimensional space plus 1 of time. But what if a universe evolved? With 4, 5, or even 10 dimensions of space, movement there would look alien to us. Objects could appear and vanish from directions that simply don't exist in our world. A 4-dimensional sphere passing through our 3-dimensional reality would seem to blink in and out of existence like a ghost. This isn't pure imagination. String theory, one of the leading candidates for uniting quantum mechanics and relativity, suggests that universes with different numbers of compact dimensions may be common. Some could be vast, filled with rich structures. Others could collapse instantly, unable to stabilize. Each bubble carries its own lottery ticket of physics, its own story, its own fate. And hidden among the sterile voids and impossible worlds are rare bubbles like ours, balanced, habitable, and alive with galaxies, stars, and thinking beings. The multiverse, if real, isn't just infinite. It is infinitely varied. And somewhere, out there, beyond the edge of our cosmic horizon, other bubbles drift, strange, alien, and perhaps, just perhaps, watching us through the scars of ancient collisions. Imagine standing in a universe with more than 3 dimensions of space. In our world, we move forward and backward, left and right, up and down. That's all we know. But in other bubble universes, extra dimensions may exist, hidden, curled so tightly that we cannot see them, yet powerful enough to shape the very fabric of physics. These hidden dimensions, predicted by string theory, may control the strength of forces, the mass of particles, even the flow of time itself. To us, they remain invisible, folded smaller than an atom. But to an advanced civilization in another bubble universe, they might be tools, knobs and dials that can be turned to reshape reality. Imagine beings who understand the geometry of their own space-time so deeply that they can alter it. In such a world, physics isn't fixed. It bends to knowledge. Gravity could be reversed so that objects fall upward. Time might be stretched in one region and compressed in another. Entire landscapes of matter could be rewritten with a single manipulation of higher dimensional fields. From our perspective, these technologies would look like sorcery, zones where reality itself changes its rules. The anthropic principle tells us that only a tiny fraction of bubble universes will ever reach this stage. Most are sterile deserts where complexity never forms. That makes intelligent life not just rare, but unimaginably precious in the infinite multiverse. If advanced civilizations exist beyond our bubble, they may have powers we struggle to name. Yet, perhaps we don't need to look beyond our horizon for such exotic possibilities. Strange, reality-bending structures may exist right here, inside our own universe. Take black holes, the monsters of space that devour everything. But hidden in Einstein's equations is a mirror solution, a shadow twin, the white hole. Where black holes swallow, white holes erupt. They spew matter and energy so violently that nothing can ever fall in. Imagine a cosmic geyser blasting galaxies, worth of material into space. The mathematics that predict black holes also predict white holes. In fact, solving Einstein's field equations produces two solutions, one describing the inward collapse, the other an outward explosion. A black hole is like watching a film of matter falling forever inward. A white hole is the same film played in reverse, matter racing outward, unstoppable, untouchable. Some scientists have wondered, could the most violent events we see in the universe be white holes in disguise? Consider gamma-ray bursts, which release more energy in seconds than our sun will produce in its entire lifetime. Or quasars, blazing brighter than 1 trillion stars from regions no bigger than our solar system. Mainstream science explains them as matter falling into supermassive black holes, heated to extreme temperatures before vanishing past the event horizon. But what if some are explosions from white holes, cosmic furnaces where creation outruns destruction? There's a problem. White holes, if they exist in our universe, would be unstable. The instant matter approached, the eruption would collapse, flipping into a black hole. This may explain why astronomers have never seen clear evidence. But in other bubble universes where the rules of symmetry differ, white holes might be stable and common. Cosmic factories endlessly producing galaxies, stars, even whole universes. Some cosmologists even propose that the Big Bang itself was a white hole event, our entire observable cosmos bursting from a single eruption in higher dimensional space. And perhaps black holes are more than tombs. Some theories suggest that material falling into a black hole here could emerge from a white hole in another universe, linking realities through cosmic tunnels. If true, every black hole might be a doorway, a hidden artery of the multiverse. But white holes aren't the only exotic scars left by the early cosmos. Imagine a crack in reality, so thin it makes a proton look colossal, yet so heavy that a single inch of it outweighs Mount Everest. These are cosmic strings, one-dimensional defects formed in the newborn universe. The analogy is simple. When water freezes into ice, it sometimes leaves cracks where crystals don't align. The early universe froze too, not into ice, but into the fabric of space-time itself. As the universe cooled and fundamental forces separated from one another, imperfections formed along the boundaries. Those imperfections became strings, stretching across the cosmos. Cosmic strings defy common sense. They would be no wider than a proton, but infinitely dense. Their gravity so immense, it bends light like glass. A mile of string would outweigh Earth itself. If they exist, they cannot be destroyed without rewriting space-time itself. They are not matter. They are topology, the geometry of existence etched in lines across the universe. Some strings could be short loops, buzzing and vibrating like cosmic wires. Others could stretch across the entire observable universe, reaching beyond into regions we will never see. As they move, oscillate, and collide, they would radiate gravitational waves, ripples in space that our instruments might already be detecting. The nanograv collaboration, which listens to pulsars, nature's most precise cosmic clocks, recently reported timing variations that may be the fingerprints of cosmic strings. If true, it means these primordial cracks still thread our universe, influencing galaxies, bending light, and whispering across time with the echoes of creation itself. Cosmic strings could even have seeded the large-scale structure of the universe, drawing ordinary matter and dark matter into their gravitational wells. Imagine galaxies forming not randomly, but along invisible scars in the cosmic fabric. Entire clusters, superclusters, and walls of galaxies could be the children of ancient strings born in the first heartbeat of reality. We are left with a haunting thought. Our universe may still carry wounds from its birth. White holes, cosmic, strings, higher dimensions, all reminders that what we see is only the surface. The deeper truths of reality may be stranger than anything we dare imagine. If cosmic strings truly lace through our universe, they may do more than mark scars from creation. They might act as bridges between worlds, threads binding separate realities together. Along such strings, information itself could travel. Imagine electromagnetic signals racing along networks of cosmic filaments, carrying whispers between universes otherwise sealed off from one another. A hidden multiversal internet woven from the raw fabric of reality. The search for these elusive strings continues on multiple fronts. Physicists scour gravitational wave data for the faint tremors of vibrating strings. They examine the cosmic, microwave background, searching for distortions that betray ancient filaments cutting across the early universe. Astronomers map the large-scale structure of galaxies, looking for alignments too straight, too precise to be natural. Finding cosmic strings would prove that reality contains more than matter, stars, and galaxies. It contains scars of physics itself, stretching into dimensions we've only begun to imagine. But strings may serve an even stranger role. Under certain mathematical solutions to Einstein's general relativity, two black holes spinning in perfect synchronization could rip open a shortcut through space-time. A tunnel where distance loses all meaning. A wormhole. This isn't fantasy. It falls straight out of the mathematics. But to keep such a tunnel open, the universe demands impossible engineering. You'd need two black holes, each electrically charged, balanced with exquisite precision so they neither merge nor repel. And then, cosmic strings. These ultra-dense filaments could serve as scaffolding, holding the wormhole throat open against its natural collapse. Strings thinner than protons but heavier than worlds would act as cosmic braces, preventing the tunnel from snapping shut. The result? A stable passage between two regions of space-time. Enter one mouth, and you could emerge instantly from the other. No matter if the exit lies across a galaxy, across the universe, or even inside another bubble reality. Travel time? 0. Here's where the multiverse returns to the stage. If cosmic strings indeed stretch across eternally inflating space, reaching from one bubble to another, then wormholes could link separate universes. Step into one, and you might emerge where gravity repels instead of attracts, where chemistry runs in reverse, where time itself flows at a different rate. It would feel like walking through a door from one dream straight into another. Yet even these theoretical wormholes face catastrophic instability. The cosmic strings holding them open would bleed energy through gravitational wave radiation. Within microseconds, most tunnels would collapse. Some theories suggest that exotic matter, particles with negative energy density, could stabilize them. If such matter exists, wormholes might persist for seconds, minutes, maybe indefinitely. Advanced civilizations, if they inhabit the multiverse, may already wield this technology, taming wormholes as highways across galaxies or even as portals between realities. If so, the barriers of cosmic isolation fall. Expansion may push universes apart faster than light, but wormholes would stitch them back together. A cosmic web of tunnels could connect realities, forming a network where information, matter, even entire civilizations flow freely between universes. A multiverse not of separation, but of connection. But not all theories about other realities involve tunnels. Some suggest that a parallel universe sits closer than we imagine, so close it's a reflection of our own, a mirror twin where time itself runs backward. The idea stems from a deep symmetry in physics. Most of the universe's fundamental laws don't care about direction. Play the tape of an object falling and reverse it. Both sequences obey gravity's equations. The laws of electromagnetism, quantum mechanics, even relativity, all are time-symmetric. But something breaks this balance: entropy. In our universe, entropy always rises. Coffee cools, glass shatters, the dead do not return. This is the arrow of time we all experience. Yet some cosmologists, including Sean Carroll, propose that the Big Bang created two universes at once: ours, where entropy rises forward, and a mirror, where entropy rises backward. To us, their reality would look reversed, but to them, it would feel perfectly normal. Picture watching a life unfold in reverse. People grow younger, memories unlearned, until all reduces to infancy. That's how their universe would appear from our vantage point. But its inhabitants, made of antimatter instead of matter, wouldn't perceive anything strange. To them, entropy still increases, stars still burn, life still evolves, just on a temporal arrow pointing opposite to ours. In this mirror cosmos, stars shine with anti-hydrogen and anti-helium. Anti-planets orbit anti-suns. Civilizations of antimatter beings might gaze into their skies, believing they too live in the only reality. If we could somehow communicate, the messages we send forward would reach them in reverse. To shake their hand might annihilate us both, matter meeting antimatter in a burst of pure energy. Two universes, born together, diverging in opposite directions of time. Their symmetry forever hidden from one another, except in the equations of physics that whisper their shared origin. They would live their lives in complete normalcy, never suspecting that their entire existence was the mirror, opposite of ours. In their eyes, we would be the alien ones. Our matter, our chemistry, even the flow of time itself would appear unnatural. The mirror universe hypothesis doesn't just explain the absence of antimatter in our cosmos, It offers a natural solution to one of physics's greatest puzzles, the arrow of time. Why does time relentlessly push forward? Why does entropy always rise? In their universe, time runs the other way, and together, both universes balance the cosmic equation. Some scientists take this further, proposing that dark matter, that invisible substance outweighing normal matter 5-to-1, could be ordinary matter leaking from the mirror universe. The two realities might be gravitationally linked, pulling on each other while remaining electromagnetically invisible. We cannot touch them, cannot see them, but we feel their weight. And this mirror universe is only one possibility among countless parallel realities predicted by modern physics. General relativity tells us that space itself isn't rigid. It bends, it stretches, it twists. Most people picture the universe as flat, like an endless sheet of paper. But in reality, cosmic geometry can vary dramatically. Our observable universe appears flat on the largest scales. Parallel lines never meet, triangles sum to 180 degrees, and cosmic structures spread evenly across the void. Yet other bubbles in the multiverse could have entirely alien geometries. Imagine a universe with negative curvature, shaped like a hyperbolic saddle stretched across infinity. In such a reality, parallel lines would never stay parallel. They'd diverge endlessly. Triangles would never add up neatly. The shortest path between 2 points wouldn't be a straight line but a warped curve, bending away from where you expect it to go. Navigation in such a cosmos would be profoundly disorienting. A spaceship might think it's flying straight, only to veer sideways along a geometry its pilots could barely comprehend. The very structure of galaxies would unravel. In our flat cosmos, matter clumps together to form the cosmic web, filaments, of galaxies tied by gravity and dark matter. But in negatively curved space, distances stretch faster than gravity can pull. Spiral galaxies would have trouble forming. Orbits would warp into unstable hyperbolas. Star systems themselves might tear apart under geometry's invisible hand. Civilizations born in such a universe would face challenges we can hardly imagine. Their science would be written not in Euclidean geometry, but in hyperbolic equations. Their physics would incorporate curves where we see straight lines. Their technology, their navigation, even their architecture would reflect an alien understanding of space itself. And perhaps, just perhaps, regions of negative curvature already exist inside our own cosmos. Invisible pockets left over from cosmic inflation, zones warped by exotic matter with unusual gravitational properties. String theory goes further, predicting 6 hidden dimensions curled so tightly that we can't perceive them. If any of these dimensions have negative curvature, they could quietly influence particle physics, altering fundamental forces in ways we still misinterpret as mysteries. But geometry is only one variable in the endless dice rolls of creation, because while you've been listening to these words, trillions of new universes have come into existence. This is the secret of eternal inflation. The same process that birthed our bubble universe never ended. It continues everywhere, always. Inflation is a machine, simple in design, yet infinite in consequence. It operates on one field, the inflaton, a cosmic energy that stretches, space faster than light. Quantum fluctuations constantly jostle this field up and down. When it falls below a critical threshold, inflation halts in that region. The stored energy transforms into matter and radiation, igniting a hot Big Bang. A bubble universe is born, but inflation never stops in the surrounding regions. They keep expanding exponentially, faster than any signal could ever cross. Inside them, more quantum fluctuations occur, triggering more bubble births. The cycle feeds itself endlessly. The numbers defy comprehension. Every second, the volume of inflating space multiplies by colossal factors, not 10, not 1,000, but numbers raised to power so vast they dwarf human imagination. In that ever-growing expanse, new universes blossom faster than bacteria, multiplying in a petri dish that doubles in size every instant. No matter how many bubbles form, the machine always runs ahead, generating more empty space, more opportunities for creation. Each bubble is an isolated experiment. Once it forms, inflation walls it off, cutting it from the rest of the multiverse at faster than light speeds. That bubble will never communicate with another. It will live, evolve, and die alone, governed by its own randomly chosen laws of physics. Some will contain 10 dimensions. Others will split time into branching directions. A few may even allow consciousness to shape matter directly. And then comes the strangest consequence of all. Because quantum mechanics limits the number of ways, matter can arrange itself in a finite volume. With infinite bubbles, the mathematics become unavoidable. Identical copies of our universe must exist. Somewhere beyond our cosmic horizon, another Earth orbits another sun in another galaxy. On that Earth lives another version of you, with the same memories, the same choices, the same story. Not just once, not twice, but infinitely. The eternal inflation machine doesn't just make universes, it makes copies. Exact duplicates of our reality, repeated endlessly across the multiverse. And in those infinite copies, the smallest differences ripple into entirely different histories. Somewhere, another you chose a different path, said yes instead of no, or never heard these words at all. This is the true consequence of eternal inflation. Not just universes without end, but lives without end. Infinite variations of you. Infinite variations of us. Every possible variation of history. Every alternative choice you could have made, every world where events diverged even by a fraction, is realized in the endless sea of bubble universes. Physicist André Linde, one of the fathers of inflation theory, calls this the ultimate Copernican revolution. For centuries, humanity believed Earth was the center of the cosmos. Then we learned our planet was just one among many orbiting a star. Then we discovered our star was just one among billions in the Milky Way. Later, that our galaxy was just one among trillions. And now, Linda argues, even our entire universe may be nothing more than a speck in an infinite frothing sea of realities. This realization shatters every lingering sense of centrality. We are not the center. Our universe is not the center. Reality itself has no center, only endless variation. Some of those variations are tame, others are nightmarishly alien. The eternal inflation machine produces universes with 10 spatial dimensions instead of our familiar 3. To us, trapped in length, width, and height, the thought is nearly impossible. Our brains evolved for survival in 3-dimensional landscapes, not for perceiving higher geometry. We can barely imagine a 4th spatial dimension, let alone 6 or 10. But string theory demands them. According to this framework, the fundamental notes of reality, tiny vibrating strings, only make sense mathematically in at least 10 dimensions of space-time. 6 of them remain curled so tightly that we cannot see them, like the hidden width of a garden hose viewed from a distance. In some bubble universes, however, these dimensions might not be curled at all. Imagine a cosmos where beings move freely, through 10 directions of space. A sphere in that reality would cast bizarre shadows in ours, appearing as shifting, vanishing, reappearing forms, because most of its mass would exist outside the limits of our perception. A native of such a universe could step toward you from a direction that simply doesn't exist here, appearing to materialize from nothing, then vanish just as easily. The physics of such realms would be unrecognizable. Gravity, which in our universe extends across 3 dimensions, would spread across 10, weakening so drastically that galaxies might never form. Stars might flicker briefly or fail to ignite altogether. Yet other forces, perhaps exotic cousins of electromagnetism predicted by string theory, could dominate instead, sculpting matter into strange structures that obey geometries beyond our imagination. Hyperspheres that invert themselves, bottles with no inside or outside, and forms that exist simultaneously in multiple locations. Civilizations in such universes would wield technologies like sorcery from our perspective. They could store infinite data in finite space by writing it into extra dimensions. They could vanish from one location and reappear instantly in another, not through faster-than-light travel, but by cutting across higher spatial directions, a shortcut forbidden to us. Some string theorists suggest that our own universe is just a 3-dimensional membrane or brain, floating inside a higher dimensional bulk. Countless other membranes might drift nearby, invisible yet separated from us by only a fraction of a millimeter in the curled dimensions. In this view, dark matter, the unseen glue outweighing normal matter 5-to-1, could simply be gravity leaking from parallel brains. The missing mass of our cosmos may be evidence of neighboring universes tugging on ours, but even in our own bubble, mysteries persist, mysteries that defy reason. Consider this: empty space weighs more than everything in it. It sounds absurd, but quantum mechanics proves it. What we call a vacuum isn't empty at all. It seethes with virtual particles flickering into and out of existence billions of times per second, in time frames so short no clock can measure them. Each fluctuation carries energy. Collectively, these fluctuations generate a staggering energy, density. How staggering? If you gathered the quantum vacuum energy inside a single coffee cup, the total would exceed the mass energy of every visible star and galaxy in the universe combined. Here's the paradox. That amount of energy should bend space-time so violently that our universe would collapse into a dense ball smaller than an atom. Yet it didn't. Instead, our cosmos has expanded for nearly 13.8 billion years, and on the largest scales, space looks nearly flat. Something is canceling out this vacuum energy with impossible precision. Physicists call this the cosmological constant problem, and it's arguably the greatest unsolved riddle in theoretical physics. Other bubble universes may have entirely different solutions. In some, the cancellation never happens, and the vacuum energy crushes reality before the first atom can form. In others, the vacuum energy runs negative, accelerating expansion so violently that galaxies never coalesce. A few universes may have quantum vacuums that fluctuate chaotically, rising and falling randomly. Imagine living in such a reality. One day, space curves inward, pulling stars together like invisible black holes. The next, it curves outward, flinging matter away in bursts of anti-gravity. In that universe, planets might suddenly veer off their orbits. Stars might surge closer or retreat without warning. Entire galaxies might twist and shear apart as they pass through regions of fluctuating vacuum. To survive, any advanced civilization would need unimaginable technology, cities designed to flex with shifting geometry, ships with navigation systems that account for constantly mutating laws of physics. And here's the strangest speculation. Some theorists wonder if consciousness itself might influence these vacuum fluctuations. The infamous observer effect in quantum mechanics shows that measurement alters reality at the smallest scales. Could awareness ripple upward, subtly steering the quantum froth that defines existence itself? If true, then intelligence wouldn't just inhabit the universe. It would help shape it. In some bubble universes, the power of consciousness itself isn't just symbolic, it's physical. Imagine a cosmos where awareness bends reality, where a collective thought reshapes the very laws of physics. In those worlds, meditation might alter gravity. Entire societies could harness shared intention to build mountains, calm storms, or even rewrite time itself. To us, it sounds like mysticism. To them, it would be engineering. Such observer-dependent physics may not be confined to distant bubbles. The key could be hiding inside one of the most terrifying objects in our own universe, the black hole. Every time a massive star dies, it collapses under its own weight. The result is a prison of gravity so strong that not even light can escape, a singularity wrapped in a one-way surface called the event horizon. From our perspective, a black hole looks like a devouring monster, a cosmic vacuum cleaner that swallows stars whole. But what if that's only half the story? Mathematical analysis of Einstein's equations reveals something extraordinary. Inside the horizon, the collapse may not end in destruction, but in creation. Instead of crushing matter into nothingness, the implosion could ignite a new Big Bang, a pocket universe expanding beyond our reach. Picture it. From the outside, the black hole appears frozen in time, silent, unchanging. But on the inside, time flows normally, space stretches, matter transforms. A whole new cosmos could be growing behind that black veil, invisible to us, yet alive with galaxies, stars, and worlds. Physicist Lee Smolin took this further with his radical idea of cosmological natural selection. What if black holes don't just create universes, but actually shape which universes survive? In his theory, each new bubble birthed inside a black hole inherits slightly different physical laws. Universes that produce more black holes generate more offspring. Over countless generations, physics evolves to favor stars massive enough to collapse. By that logic, our universe is a descendant, the child of black holes in a parent cosmos. And our physical constants exist not by chance, but because they were the most successful recipe for reproduction. If true, then the universe is not a sterile void. It's a cosmic family tree, endlessly branching across eternity. Some bubble universes might resemble stellar hothouses, with physics so efficient at black hole creation that they spawn billions more than ours. Each of those black holes could cradle new realities within, multiplying the multiverse in an endless cycle of birth, collapse, and rebirth. But not all gravitational mysteries come from the depths of black holes. Some are written across the largest maps of space we can make. Take the Great Attractor. Our Milky Way galaxy, along with thousands of others in our local group, is moving through space at more than 1 million miles per hour. Not randomly, but in a single direction, straight toward the Hydra constellation. It's as if an invisible magnet is pulling our entire region of space toward it. Astronomers first noticed this motion in the 1970s. By the 1980s, it became clear that the tug came from something huge, a structure with the mass of at least 10,000 Milky Way galaxies. Yet when scientists pointed their telescopes at the spot, they found nothing unusual. Just ordinary clusters of galaxies, nowhere near massive enough to explain the pull. Part of the mystery comes from the so-called zone of avoidance, a band of the sky shrouded by the dust of our own galaxy. That dust blocks our view, like a curtain drawn across a theater stage. But even accounting for it, the numbers don't add up. Something colossal is hiding there, invisible to our instruments. And the great attractor itself is being dragged, even further, toward an even larger structure, the Shapley supercluster. This titanic formation contains the equivalent of 10 quadrillion suns bound together in a web of gravity. Yet even Shapley may not be the end of the chain. New mapping of galactic motion reveals something more unsettling. Our entire observable region, millions of galaxies spread across hundreds of millions of light-years, appears to be streaming toward something even larger, something that lies mostly beyond our cosmic horizon. Scientists call this phenomenon dark flow. Think of floating in a river. You can feel the current tugging you forward, but the waterfall pulling you lies just beyond sight, around a bend. You cannot see it, but you know it's there. That's what's happening to us. The galaxies we can see are rushing toward something massive and unseen, a gravitational anchor outside the limits of our observation. Some cosmologists suspect that these hidden titans are fossils of inflation, vast concentrations of matter, birthed in the first split second after the Big Bang. Others propose something stranger still. Objects existing in higher dimensions, exerting their weight across the walls of our universe like fingers pressing against the surface of a balloon. If true, then the great attractor and dark flow may be our first hints of other universes bleeding into ours. Forces beyond our perception, tugging on our galaxies, whispering through the fabric of reality, and in some of those universes, the rules of physics themselves would be reversed. A place where the most basic forces, gravity, electromagnetism, even the flow of time, follow laws completely alien to our own. Let me shatter a basic assumption about reality. In our universe, opposite charges attract while like charges repel. It's the foundation of every atom, every molecule, every breath you take. But imagine a bubble universe where this law is flipped, where like charges attract and opposites repel. In such a place, chemistry as we know it would be impossible. Protons, each carrying a positive charge, wouldn't huddle together inside atomic nuclei. Instead, they'd violently reject each other like magnets forced north to north. No atom could ever form. No molecules, no water, no DNA. Life, at least, in our familiar sense, could never exist. But this reversal wouldn't mean a barren void. Instead, it would give rise to entirely new forms of matter. Picture particles with the same charge clustering together into crystalline assemblies. These bizarre structures, held in a delicate dance between gravitational pull and electromagnetic push, might resemble hollow shells with intricate internal lattices, matter shaped not by chemistry, but by the competing tension of cosmic forces. On the largest scales, such universes would be alien beyond recognition. Stars wouldn't form from gravity-crushing gas. Instead, they might ignite through electromagnetic attraction, pulling plasma into blazing orbs that shine with unfamiliar colors. Galaxies wouldn't swirl in spiral arms like our Milky Way. They could form geometric webs, their light bent and confined by electromagnetic scaffolding. And it doesn't stop at reversed polarity. Some bubble universes may amplify electromagnetism until it's millions of times stronger than in our reality. Atoms there would be enormous, their bonds blazing with energy. Molecules could lock into hyper-complex architectures, exotic chemistries, giving birth to life forms stranger and more intricate than anything we could imagine. Other universes might weaken electromagnetism until atoms shrink to ghostly points. Chemistry would collapse into the realm of pure quantum mechanics. Matter would behave more like a fluid of probabilities than solid particles. Intelligence in such a universe might not evolve from neurons firing in biological brains, but from vast fields of quantum coherence, a kind of hive mind woven directly into the fabric of reality. The possibilities grow even more alien. Some universes could split electromagnetism into two distinct forces, one purely electric, one purely magnetic. Civilizations there would build technologies beyond our comprehension, machines that respond only to magnetism, or structures powered exclusively by electricity, each obeying rules utterly foreign to us. And in other universes, entirely new forces may exist. Invisible bonds binding matter in ways we cannot yet conceive, giving advanced beings the ability to sculpt matter, travel across light years instantly, or compress energy into patterns of living information. But even in all this unimaginable diversity, there may be one common thread: dark matter. Here in our universe, dark matter forms an invisible skeleton. It shapes the great cosmic web, colossal filaments stretching across billions of light years, guiding the growth of galaxies and bending light from the furthest stars. Without this scaffolding, the universe would scatter like sand in the wind. Yet, what if this web doesn't end at the edge of our observable universe? What if it continues, stretching into other bubbles, weaving them together into a vast multiversal network? Picture it like a forest. Each tree seems to grow alone, yet beneath the soil they're bound together by a living root system of mycelium. Nutrients and signals pass silently from one tree to another. The forest breathes as one. The multiverse may work the same way, with dark matter filaments acting as the hidden roots connecting separate universes. If so, then gravitational ripples could travel along this invisible network, leaking from one reality into another. The mysterious dark flow dragging entire galaxy clusters toward unseen regions may be nothing more than our universe tugged by structures anchored in another, and if the filaments are stable, they could serve as bridges. Gravitational waves might carry encoded information through them, allowing advanced civilizations to send messages across the multiverse. Imagine a cosmic internet spanning infinite realities, civilizations whispering across the void through channels of dark matter. Some physicists even suggest that dark matter may exist in higher dimensions, intersecting with countless three-dimensional universes at once. To us, it appears as ghostly scaffolding. To them, it could be the very backbone of reality itself. Now consider the implications. If advanced beings ever learn to engineer dark matter, they could sculpt the multiverse itself, redirect the flow of galaxies, stabilize wormholes, even create artificial bridges between universes. The cosmic web, normally silent and invisible, would become a highway, a vast transportation network for inter-universal travel. And here's where the mystery deepens. Some scientists believe consciousness itself could play a role. Quantum mechanics already shows us that observation changes reality. A particle exists in many states at once, until someone measures it. Then, in an instant, it chooses. Now imagine universes where this effect is magnified, where thought doesn't just influence the microscopic, but the macroscopic. Worlds where meditation bends gravity, where focused awareness alters the constants of nature. where collective consciousness could rewrite the laws of physics and build reality as easily as we build cities. In such universes, consciousness wouldn't be a byproduct of matter. It would be the master force, the ultimate architect of existence. The famous double-slit experiment showed us something unsettling. Electrons don't behave like tiny billiard balls rolling along fixed tracks. They move like waves traveling through two paths at once, until someone looks. The instant an observer measures them, the wave of possibilities collapses into a single outcome. This is the observer effect, and it implies something profound. Consciousness itself shapes reality. Here in our universe, the effect is subtle. You can't shift the orbit of the moon by staring at it, or will mountains into moving with your thoughts. Quantum effects fade away when scaled to warm, massive objects. But what if that's not universal? What if in other bubble universes, quantum uncertainty never collapses unless a mind is watching? Imagine a cosmos where conscious beings don't just observe reality. They create it. Stars ignite because they believe they should. Galaxies bend and twist under the weight of collective attention. Entire landscapes shift with the meditations of civilizations. In such places, technology wouldn't be built from steel or silicon. It would be built from awareness itself. Minds trained like instruments, tuned to bend reality as easily as we bend metal. Some cosmologists take this further, suggesting that no universe exists at all without observers. This participatory universe hypothesis argues that without consciousness, all possible realities remain suspended as ghostly quantum potentials. Only when awareness arises does the fog collapse into a definite physical world. If true, then the multiverse is not just vast, it's alive with awareness. And here's where the boundaries dissolve into something even stranger. What if our reality is not physical at all, but computational? The simulation hypothesis suggests that every star, every atom, every thought in your head might be the output of a vast, unimaginably powerful computer. The rules of physics? Merely the programming shortcuts of a cosmic engine designed to conserve processing power. The speed of light might be a rendering limit. Quantum uncertainty might be code compression, and if such simulations are possible, then base reality would contain only a handful of original universes, but an almost infinite number of simulated ones. By sheer probability, that means we are more likely to be living inside a simulation than not. The implications spiral upward like Russian dolls. If our universe is simulated, then the beings who built it might themselves live in a simulation, and their creators might also be simulated. Layer upon layer, world within world, an infinite hierarchy of realities, each one believing itself to be the base. Somewhere, perhaps, a final layer exists, or perhaps the chain never ends. And yet, whether base or simulated, every universe faces the same destiny: death. Our own cosmos is drifting toward heat death. Dark energy pushes galaxies apart at accelerating speeds. In the far future, every galaxy will slip beyond every other's horizon, leaving islands of isolation scattered in a vast black sea. Stars will burn out. White dwarfs will fade. Neutron stars will dissolve through proton decay. Even black holes will vanish, evaporating over unimaginable spans through Hawking radiation. What remains will be a thin mist of particles spread across endless dark, a silent graveyard of reality. But endings are never final. Just as forests, Burned by fire give rise to new life. The death of a universe may sow the seeds of another. Quantum fluctuations in the empty void can spark new inflationary bubbles, new big bangs. From nothing, new realities bloom. Physicist Roger Penrose goes further, proposing that the heat death of one universe becomes the big bang of the next. Like links in an eternal chain, each cosmos gives birth to its successor. The faint fingerprints of past universes may even be etched into the cosmic microwave background, silent messages from worlds before ours. And here lies the most staggering possibility of all. Consciousness may not just survive these cycles, it may guide them. Advanced civilizations, staring down the death of their universe, might learn to encode knowledge into the quantum fluctuations that seed the next cosmos. Their thoughts, their histories, their essence could ripple forward, shaping the physics of universes yet unborn. In this way, awareness achieves a form of immortality, passing like a torch from one reality to the next. The cycle becomes clear: birth, growth, death, rebirth. Not of one universe, but of infinite universes, stretching across eternity. So when you look up at the night sky, when you count stars and galaxies, when you imagine the edge of the observable universe, know this: what you see is only the smallest spark in an endless storm. Beyond the cosmic horizon lies a reality where every possibility becomes actual, where every dream becomes real, where consciousness itself might be the architect of existence. And in that eternal cycle, one truth echoes: we are not witnessing the end. We are witnessing infinity in motion.